Hi again. We considered this problem at the end of the last video. We, I asked you to find z subscript 0.05, which is 5%. So it means top 5% value. So top 5% equals to the 95 percentile. So percentile calculates from the bottom. This notation calculates from the top. And on Excel, you have to use uh, the percentile. You have to enter 0.95 to obtain this value. It's very annoying and inconsistent, uh, like between notation and Excel and mathematical definitions. But I don't like it either. But I have no power. I'd like to change the notation by myself. I can do better, but I have no power. Anyhow, the answer is 1.64. It's top 5% value. It's top 5% value, and we have this. By the way, we have the symmetry. So when you have the top 5% value, the bottom 5% is can be obtained automatically. Like if because the top 5% is 1.64, the bottom 5% value is minus 1.64, right? So therefore, what we have here is we know top 5% and bottom 5%. So you have this form. It's a little bit stupid notation. I don't know. I have to check it why it looks like this. Anyhow, between plus minus z alpha over 2, z alpha over 2 is top alpha over 2 probability value and bottom alpha over 2 probability value. So here we have 5%, top 5% value 1.64, bottom 5% value minus 1.64. So in between that, we have 90%. 90%, right? The missing probability 10% is split between the top and the bottom. So this is how we use the standard normal distribution. Just to wrap up, we learned how to calculate the CDF and how to calculate the percentile. So Excel tells you these two. These are embedded in Excel. And from the CDF or the percentile, you have to calculate what you want. Like if you are interested in probability between 2 points, or if you are interested in value that's within top certain percentage, then you have to transform the results as the way you want. Okay, okay. If you need more exercise, you can play on Excel. Just it's easy and interesting thing to do, and I believe most of you should be fine. Just practice more if you want, if you need. So okay, then I will assume that we know everything about the standard normal distribution at this point. By the way, that's just uh, one special case of normal distribution. So standard normal distribution is one special normal distribution with the mean equals to 0, variance equals to 1. Then it it does not work. How can we handle a normal distribution with different parameters? What happens if the mean was not 0 or if the variance was not 1? My answer is what's nice about the normal distribution is always we can standardize any non-standard normal distribution into the standard normal distribution. Always. So the starting point is again going back to chapter 3. right? We in chapter 3 and chapter 4, we learned the linear transformation and its properties. And we, you may remember these forms. If y is a linear function of x, we have expectation of y that preserves the linear relationship. Variance of y multiplied by a squared, but not affected by the additive term. Standard deviation is multiplied by a, which is consistent with the unit scale, but it's not affected by the constant additive constant either. So addition does not affect variance and standard deviation, and multiplication does affect the variability, variance, and standard deviation. Why do we use it? Because the expectation, the mean, and the variance are the parameters for normal distribution. So, in addition to these three formulas, there is a fourth uh, property of a linear transformation. That is, if the original random variable is normal, then the linear transformation is also normal. The normal distribution is also preserved. It's just a matter of how concentrated or how spread out or where the center is. So bell curve, the shape of the bell curve may change by the parameters, but basically all the bell curve properties are preserved after linear transformation. This is very nice property actually, and you may think it's obvious, but this property does not hold for most of the probability distributions. It's a very special and nice property for a normal distribution. Therefore, if the original random variable is normally distributed with parameters mu and sigma squared, so mu is the mean, sigma squared is the variance, which means sigma is the standard deviation. So you may obtain the new random variables mean and variance and standard deviation using the formula. So the mean equals a times mu plus b. Just put uh, plug in mu, plug mu into the mean, and variance a squared sigma squared, because variance of x is sigma squared, and standard deviation is simply a times sigma. Therefore, if you combine everything, y is a normal distribution, and its mean is given by the first line, this one, and its variance is given by the second line. So you know everything. You know that y is normally distributed, and you know its parameters, which means you know everything, right? This is very nice, one of the most important properties of the normal distribution. All the normal distribution satisfies this. And so we are going to use this linear transformation idea to standardize non-standard normal distribution. So the idea is we would like to choose A and B. So transformation is what we do. We may choose A and B, but especially in particular, we are interested in the case where the resulting random variable is a standard normal distribution. That means if we want the mean of the new random variable equals to 0 and the variance equals to 1, so that y follows the standard normal distribution, right? If you can choose A and B that satisfy these two conditions, then y is standard normal distribution. Mean is 0, variance is 1. It is easy to see what are A and B. The answer is A has to be 1 over sigma. so that the variance equals to 1. So original variance is sigma squared. So to cancel it out, you have to have 1 over sigma squared here. So that, therefore, A equals to 1 over sigma. And B is coming from here. A mu plus B must be 0. So, and we know A equals to 1 over sigma. Therefore, B is minus mu over sigma. So that both are, these are cancelled out and equals to 0. Or in the end, the linear transformation takes this form. Y is x minus mu over sigma. This is the standardized score we learned in chapter 4. And it's easy to understand. You have to subtract the mean so that you are recentering the distribution around 0. You recenter, you make the center at 0, and then divide by sigma. If sigma is too wide, if sigma was greater than 1, by dividing by sigma, you make the distribution more concentrated, more curvy. But when sigma was smaller than 1, then the original distribution must be more concentrated, then you are making it more flatter. So, do you get the idea? It's a very clever idea to standardize normal distribution. And usually we use Z. Again, Z was the standard normal distribution. And again, we use Z for this standardized random variable. So you have normal distribution. Then always you can standardize the random variable using linear transformation with deliberately chosen parameters, chosen constants. And Z itself is important. It measures how many standard deviations X is from its mean mu, right? So as X increases, Z increases too. It's a standardized score. So as X increases, Z increases too. And if X is above its mean, then Z is positive. And X is below its mean, Z is negative. And so it's exactly the standardized test score. And now we are going, okay, I will stop this video here and I am going to continue how we utilize this idea when we calculate the probability. Okay, see you in the next video and thank you for watching.